crystallite size. So many of us sometime make the misuse of this terminology. We determine the particle size. We say that the particle size from XRD is something like that. So particle size is different and crystallite size is different. So that we will calculate at the last crystallite size we will calculate after calculating the lattice constant and density by using X-ray diffraction pattern. So first of all, I just would like to bring to your notice. So this is a unit cell. So this is the smallest volume unit, and if you want to, so I will make it bold and stick, or you can make it space fill. Okay, this is the lattice, and if you just want to see the crystal structure of a bulk crystal, you can just add. So the crystal structure, bulk crystal will be bigger than the smallest unit. The smallest unit we call it as a unit cell volume. It is just like a cooking rice. So when in days we were not having the cookers. So when we were boiling the rice grains, we used to take out few numbers of grains and taste whether it is cooked or not. Likewise, if you have crystal system, bigger crystals, you don't have to solve the structures of each and every part of that crystal. You have to take small grain of it out of it, and that smallest volume that you have to focus. So this is the unit cell volume. So you have to solve the structure of this smallest unit, and then it will be repeated in all direction. So that is the only way we can solve this crystal structure. Now you can see that these are the sets of, there are planes of the atoms present in the crystal system. Now we will take basic examples. So Ap3O4, most of the time ferrites are the favorite materials of the current day students. So you can see that. So there is a plane of atom at the surface. So this plane particularly is having a parallel plane to it. So we'll go back to the XRD pattern first, and then we'll come back to the structure. So this is the XRD pattern of aluminum powder, aluminum. So in aluminum crystal, the aluminum will show the cubic crystal system. All the metals, most of the metals will have the cubic crystal system. Either it is a face-centered cube, primitive cube, or body-centered cube. Now you can see that there are different planes of atoms are there in the aluminum unit cell. In this unit cell, there are different number of atomic planes. So there is one plane. So there is another plane is there. Then third plane is there. Fourth, 5, 6. It means that there are 6 different sets of planes. Those are present in the aluminum crystal structure. 6 sets are there, having different values of interplanar spacings d1 to d6. So some plane will have the distance between the another similar planes as a d1. There will be another plane set of planes that will have the distance d2. Likewise, you have 6 sets of planes. Those are present in the unit cell of aluminum. That is why you are only getting the 6 peaks in the XRD pattern of aluminum powder: 1, 2, 3, 4, 5, 6. So if these number of planes will be more in one unit cell, you will get more number of peaks. So, so when we calculate the XRD pattern, when we collect the XRD data, what we used to get is that, I will just to show you, some of the students have sent their X-ray diffraction data. So you can see that you are getting counts. Okay. Okay, you are getting 2 theta values over here. In one column, you are getting 2 theta. You are getting intensity at this 2 theta. So now we will just copy, okay, focus on this one. 10, 10.02, 10.04, not 6, not 8, like that. So we are controlling 2 theta. So in XRD pattern, we are controlling 2 theta positions. So it means that 2 theta value. So the goniometer will help us to orient our sample to coming X-ray beams, something like this. For example, if you start your experiment at 10 degree, 2 theta value, so you can controllably go to 10 point, not 2, not 4, then not 4, something like that, and you can reach up to 80 degree 2 theta. So this is a control that we can make it on the angle of incidence by using goniometer. Goniometer is a device. It is mostly used in physics. So to control the angle of orientation of specimen. Now we are controlling this angle, and we are exposing those planes which are parallel to each other. In our crystal system, there will be imaginary planes of atoms which will be parallel to each other. So we will expose these planes of atoms to the incoming X-ray beam by changing the angle of orientation. This theta we are changing in terms of 2 theta value, so that when there is a fulfillment or satisfaction of this condition, 2d sin theta is equal to n lambda, you can see that d is limited, means d has only few values. D has only few values and wavelength is constant. N is always 1. We are changing theta. We are continuously changing. You are going, you can see that. If you initially theta will be smaller and at last theta will be larger. So this side is constant throughout the experiment. You are not changing wavelength in the experiment. If you want to change it, you can change after finishing the experiment, but that will not be applicable to your initial data. So this is constant, n is always 1. So if you change theta, d will get reduced. So means that in earlier peaks of the peaks in the XRD pattern will be of the planes which are having larger distance d in between them. The earlier peaks in XRD patterns are just because of the larger d-spaced planes. And when you will go from smaller angle to higher angle, the closely spaced d-spacing or closely spaced planes present in the crystal will reflect the X-rays by this condition, and their intensity will be appear like this one. Okay. Now this d value will not be continuous. You don't have, angle is continuously changed. You can see that 10, 10.02, 10.04, not 6, not 8, then 11, 10.1, something like that, up to 80. But D, there are certain sets of planes present in the crystal. So if you change the crystal, for example, if you change AL by FE, the size of AL will be different, size of FE will be different. So suppose that these are the two atomic planes which are adjacent with each other. So this is Fe, this is also Fe. So if this D is DFE, size of Fe is different than the size of AL. So this D will be different than the D present in aluminum lattice. In aluminum lattice, there will be a particular set of D values. So you will have 6, 7, 8, 9 or 10 D values. So when your angle will reach at certain position, then and then only this equation will be satisfied and your peak will appear. So you can calculate this spacing by using this equation. For example, we will calculate this spacing in next uh, after next 10-20 minutes, because we have to solve it for calculation of lattice parameter. Then we will see. Okay, now we will. Okay, this is one more concept where the Bragg's law is negative one. For example, so this is the first layer of atom, and there is a second layer of atom is there. So first beam of light, this is the second beam of X-ray. So first beam of X-ray, second beam of X-ray, it is reflected from this plane with angle theta. The second beam reflected from the third plane, angle is the theta. So they are in phase after diffraction. You can see that in phase means crest and crest superimpose with each other. But if there is one more plane present in between these two planes, so the wave, suppose this is a third wave. So the wave that is reflected from this midway plane, that will be out of phase with the first wave. So this will cancel this one. So the material is crystalline, planes are there, repetitive order of atom of arrangement is there. But because of this particular special symmetry, the constructive interference of these two beams will be disturbed by the constructive interference of these two beams. Okay, and the totally you get nothing at the end. We call it as a missing reflection. So it is a special symmetry case, body centered cubic. We will come back to it, because when we will solve some examples in body, in primitive cube, first peak is 100 always. In body centered cube, 110 is the first peak, 100 is absent. So why 100 is absent? Because you can see that this is 100 plane, this is 100 plane. In between 100 plane, there is a 200 plane is there. This 200 plane, in this case here you have 200 plane. Okay, later on. Okay, this 200 plane is there, that will cancel the reflection from these 100 planes. So that is why you cannot get the intensity of 100 peak in body centered cube or face centered cube. We will see that afterwards. Now we have to take an example of that aluminum XRD pattern. Okay. By using X-ray diffraction, we can determine the type of lattice. I have already told you in the morning, we have 7 crystal systems: cubic, tetragonal. Help of X-ray diffraction pattern, and we can determine what type of lattice is there, and we can determine the lattice constants. High symmetry can lead to reflection being systematically absent from the data set that we had seen. Body centered will nullify the intensity of 100. Absent reflections have no measurable intensity. The general absences determine the lattice type. For example, if you were 100 peak is not there, we had seen that this is just because of 200 plane present in our sample. So that nullifies the intensity of 100. So you can understand that if 100 peak is not seen in cubic material, it is just because of body centered or face centered lattice. So now we will come to this slide little late. So these conditions we need later on. So before that, we have to consider there is one more concept. That concept we call it as a reciprocal lattice concept. By using that reciprocal lattice concept, we can relate d. What is d? D is nothing but the interplanar distance. So distance between the two similar planes of atoms present in your crystal is nothing but the d. that we call it as an interplanar distance, that can be related to the size of A is the lattice parameter, or the it is the length of your cubic unit cell A. So that can be related to this D by this particular lattice reciprocal lattice concept by this equation h square plus k square plus L square. So I don't have much time to write all these things. Okay, it is becoming difficult. Okay. To write. So you can see that what is HKL? HKL is the index of the plane that we had determined. So very, I think initially we have determined the HKL values by considering the intercept point. So we have considered the gray shaded area as a crystal plane when that makes some intercept with the A, B, C axis. So we found out the coordinates of those axes and we took the reciprocals of those intercept, and those reciprocals are nothing but the Miller indices of the planes. So nothing but the HKL. So this HKL, so from XRD we can only get D values. We can get only D values, and we can relate this D value to the A and HKL. Now we will have some mathematical formalism for it. Mathematical method or analytical method can be used. Now you can see that you just take reciprocal of this equation. It will be 1 over D is equal to under root h square plus k square plus L square. This is reciprocal of the equation, above equation only, nothing but that. So you can write A. If you will square it, what will happen? 1 upon D square. And here h square plus k square plus L square upon A square will be there. So that is shown here. So this is the equation that is coming from the reciprocal lattice concept. Now you have Bragg's law. N lambda is equal to 2d sine theta. N is always 1. So we will just take it as 1 and we will not write it again. Square this equation. So it will be lambda square. 2 square is 4. D square sine square theta. Okay. Now in these two equation, what is common? D square is common. D square. You can see. And sine square theta. So sine square theta is equal to lambda square upon 4d square. Sine square theta is equal to lambda square upon 4d square. Now you have to combine these two equations with the plane spacing equation gives us a new relationship. You can see that 1 over d square, a square plus k square plus L square upon a square, and you can see that 4 sine square theta, this equation will be written. You can take the 4 this side and lambda this to this side. So you will have 1 over d square. 1 over d square is equal to 4 sine square theta upon lambda square. So you got the values of 1 over d square. Now this equation contains 1 over d square. So you can write at last a square plus k square plus L square is equal to 4 sine square theta upon lambda square. You can put this value of 1 over d square in this equation. So you got a new equation like this. Now you can see that in your crystal you have a set of plane. So maybe 6 set, 5 set, 10 set, 8 set, something like that. So you will have 6 different values for h, k and L. So you will have h1, k1, L1. You will have h2, k2, L2. So you have How many sets are there? Up to that you will have different number of values. So H6, K6, L6 like that. Now what we can do is that, so this equation we can mix. So you can say that, you can see that. So sine square theta, now this one, sine square theta is equal to lambda square upon 4a square. So this a you can take to this side, 4a square upon lambda square. So you take it to this side, so that will be sine square theta is equal to lambda square upon 4a square into h square plus k square plus l square. So this equation you can rewrite. So you have sine square theta. So you can rearrange this equation likewise. Now you can see that lambda is constant, 4 is a number. So that cannot be variable, it will remain constant throughout the equation. A is the size of the lattice that you are probing for that experiment, particular experiment you are doing. For example, if you are probing aluminum crystal, the A of aluminum crystal will be constant. So this term will in the parenthesis will be constant. So lambda square upon 4a square will be constant for that experiment. So what does it mean? It means that sine square theta is proportional to the sine square theta is proportional, directly proportional to the sum of h square plus k square plus l square. So from XRD data you can get only theta value at which peak will appear. So if you will find out the peak 2 theta value at which peak will appear, and if you will take from 2 theta, if you will get a theta, you can take sine of theta, then you can square that sine theta. So that is directly proportional to the sum of a square, k square, l square. Now from the initial experiments, sorry, initial discussion that we have made on the calculation of lattice spacing, okay, here you can see that the planes which are having smallest HKL values are placed away from the origin, and the planes which are having highest HKL values, they are placed close to the origin. So from this particular concept, what we can do is that we can take a ratio of HKL values of different planes, so that will tell us about the position of the plane present in the crystal. So we can scale, in other word, we can scale the index of the peak by taking the ratio of sine square theta. The ratio of sine square theta values scales the ratio of h square plus k square plus l square values of different planes. So you can see that this was our equation, this was the constant value. So this is directly proportional to this one. The sine square theta is proportional to the sum of h square, k square, l square. The proportionality shows that planes with higher Miller indices will diffract at higher values of theta. Now we will take the ratio. This ratio value scales the ratio of HKL values. Now how to do it? Actually, this is the theory. In practice, we can do it simply by taking an example of aluminum again. So now you can take out the notebook and pen as well as calculator. Yes, you can take the notebook, you can take the pen, calculator with you, and you can just solve this problem with along with me. This is the XRD pattern of aluminum. So if you will plot the XRD like this, you will understand that, okay, first peak is appeared somewhere here, and by using different types of softwares, you can find out the peak position. The first peak is appeared at 38.43 degree to theta value. Okay. Second peak is appeared at 44.67. Third peak is appeared at 65.02. Fourth is at 78.13 degree to theta. Third peak is appeared at 82.33. I will not go beyond this. So normally we can reach up to 80 or 90 degree by using laboratory X-ray sources. Now you can see that when you get X-ray diffraction pattern, so operator will tell you the lambda value of the experiment. So you can see that for this experiment 1.54 is the wavelength that has been used for X-ray diffraction experiments. Now you can see that what we can do, we can deduce so many values from this particular information. So when you get your sample to X-ray diffraction machine, you will get this kind of patterns. Now it is your duty to get the information about your sample from this pattern. So what to do? First of all, you have to find out the peak position. So you can mark the peak position by using origin or Excel, or if your laboratory will have X-ray diffraction machine, the inbuilt software will be there that will list you these values. Then second duty is that you have to find out the wavelength of diffraction experiment. Now what you have to do is that in the next steps you can index the XRD pattern. Index means when you assign HKL value to these reflections. So if you write this as a 1, 1, 1 or 1, 0, 0, if you assign these values, HKL values to this peak, this procedure is called as a indexing. So indexing can be made in two ways. First way, if your material is reported, you go to the literature and you can check the first peak of aluminum is coming 38.4 degree. Is there any aluminum material that has been tested in the literature? Okay, it is another material is there reported by X and YZ. It is giving the peak at same position and they have denoted this reflection as 100 or 111. You can use the same way, same number, you can put it here and you can just give the reference of that XYZ. Now, if your material is brand new and if it is a cube, now we are choosing this formalism for cubic system. You can see that we have used this equation, cubic system equation. For tetragonal equation is different. For orthorhomb equation is different. We will not solve the problems of tetragonal and orthorhomb in this session because it is time consuming, little bit complicated. Simple system we are handling just for sake of convenience. Now, what you have to do is that if your material is unknown and if it is cubic, you can do certain set of calculation. Very easy. And you can assign this number. It is called as a indexing of novel systems. So first step is that identify peaks, means you have to find out the peak position to theta value at which peak is appearing in your XRD pattern. Then divide this 2 theta by 2, you will get theta value. Then take sine of this theta, you will get sine theta value. Then you take a square of this one. You can take square of this sine theta value. This is x, okay. Sine square theta you will get. So now this sine square theta, what you have to do is that we have seen that if you will have sine square theta divided by sine square theta, 1 divided by sine square theta 2, so you will get a ratio of a square plus k square plus l square upon a square plus k square plus l square of the another peak. So that is why you have to take sine square theta divided by sine square theta minimum ratio. And that ratio, you know that HKL value is a full number. HKL value is a full number, that is integer. 100 is integer, 110 is also integer. So whatever ratio is there, that should appear as a full number. Integral value you should get. If you don't get integral value, you have to multiply that particular ratio with 1, 2, 3 up to the point where you get appropriate integers. Then you have to dissociate that integers into this value. So now we will go to index the XRD pattern of Aluminium. So it is here. You can see that 38.43. Can somebody tell me what will be the what will be the theta value of this one? You can just take an example. You can just take all these value. I will just take only four values out of it. Four value. So we can go to the 38.43 divided by 2. You can do 38.43. We can just spend 5 minutes because this is very important problem that you can understand so many things out of the box. Okay, 38.43 divided by 2, 19.215. 19.215. Is it visible to all of you? Hello? Is it visible or okay, okay. Okay, let me go here. The next is 44.67 divided by 2 you can do. You can take sine of it. Sine trigonometry, you can take sine. It is 0.32991. Sine is, okay, I have written sine square theta. So you can do sine theta 0.3291. Take square of it. Square 10.1083 is a sine square theta. Sine square theta. Oh, sorry. Bullshit. Okay. So this is the 19.215. 19.21 for you. Just a moment, I'm doing something. 0.3291 sine theta. It is a square of sine theta. Sine theta square. Okay. Okay, it is a square, so you can write it 0.1083. Similarly, you can do it for the next one, 44.67 divided by 2. 44.67 divided by 2, you will get 22.33 for you. Then you take sine of it, trigonometry, sine. It will be 0.3800. Write it here, 0.3800. Then you take square of it, square, 144.1444. Okay, take the next angle, 65.02 divided by 2. Why to divide it by 2? Because we want the theta value. In XRD we get 2 theta. So 32.51 is theta value. 32.51. Take sine of it. Go here and take sine. Okay, 5374. 0.5374 is a theta value. Sine theta value. Oh, sorry, 74. Okay. Now you take square of it. 0.288. 888. The last one is 78.13. 78.13 divided by 2 is equal to 39.065. 39.065. This is a theta. Then you go for sine theta. Take sine theta of it. 6302.6302. Then you go here sine square theta. Take a square of it. 0.3971. 0.3971. The last one also we will get 82.33, and beyond that we will not go. 82.33 divided by 2, 41.165. Take sign of it. 6582.65829 something is there. I will write 82 only. Take square of it. Square 0.4332. Now we will go back. So our procedure will tell us, is telling us, this is your procedure. What this procedure is telling, calculate the ratio of sine square theta divided by sine square theta minimum. So which theta is sine square theta minimum is there? This is sine square theta minimum. Just a moment. Sine square theta. This value is minimum. Okay. This value is minimum. So you have to divide this sine square theta value by this value. So this will 0.10. I will write the title of this particular column. You will get otherwise confused. Sine square theta minimum. Okay, so this will remain 1. So next you can see that 0.1083 divided by 0.10831, then you go for 0.1444 divided by 0.1083 is equal to 1.33, then 0.288 divided by 0.1039, 1083, 2.666. This is the ratio that sine square theta divided by sine square theta minimum we are getting. Last two values are there. 0.3971. 3971 divided by 0.1083. 3.666. 3.666. The last one. 0.3971. Sorry, 0.4332 divided by 0.1083. You get 4 here. Now what it is? Sine square theta divided by sine square theta minimum is nothing but the sum of h square, k square and l square. But you know that h, k, l values are integral values. They are integers, 1, 2, something like that. So these values are fractional values. So by this method, what you can do, you can multiply it by 1, 2 or 3 or 4, 5 until you get a full number. You multiply it with 2, what will happen? This 1.33 will get you 2.666. Then you multiply it all the values by 3. By multiplying it with 3, you will get 3. This will become 3 into 1.33. So this 3 into 1.33 will be something like that, 4. 1.33 into 3, 3.99 means 4, approximately 4. 2.666 into 3, you can do it. 2.666 into 3 is equal to 7.998. So you can approximate it as 8. 3.666, 3.666. You can multiply it with 3. It will be 10.998 means it will be 11. 4 into 3 will be 12. Now what are these numbers indicating to us? So it is the sum of h square plus k square plus l square. Now what you have to do is that you have to split this number 3 in such a way that it should be square of integral. So 1 square plus 1 square plus 1 square. You will get 1, 1, 1. So now this is a 4. You have to split this number in such a way that it is a 2 square plus 0 square plus 0 square. It will be 2 0 0. This is 8. It will be 2 square plus 2 square plus 0. Here I cannot write square easily, so you can just write it on your notebook. 2 square plus 2 square plus 0 square. It will be 220. 11. You can see that 3 square plus 1 square. 3 square plus 1 square plus 1 square. So it will be 9 plus 1 plus 1. So this will be 3 1 1 1. This is of 12. 12 will be something like that. So how you will split the 12 so that it can become a square of three numbers? Yes, 2 square plus 2 square plus 2 square. So this will be 2 2 2. Now you can see that first peak is because of 1 1 1. Second is 2 0 0. Third one is 2 2 0. Fourth one is 3 1 1. So you can go back to the XRD pattern. You can write it here 1 1 1, 2 0 0, 2 2 0. So this is called as indexing. So this peak will be now 1 1 1. So you can write 1 1 1. You can write it 2 0 0. You can write 2 2 0. Something like this. Then there will be 310 something was there 310 and there was a 222. So this process of assigning HKL value to this peak is nothing but the indexing. So now we have successfully indexed this XRD pattern. So in between this range, there is no unindexed XRD peak is remaining. All these peaks are getting proper value. So this indexing is called as a successful indexing. Now you can see that we have obtained HKL. First of all, we could determine either it is crystalline or amorphous. Second, we can calculate D value, that is interplanar spacing we can get from XRD. Because of n lambda is equal to 2d sin theta. Theta is known, lambda is known, you can calculate D. Second application. Third application, we can assign HKL value. We can understand which crystal plane is taking part in the diffraction procedure. Means the peak appeared in the XRD pattern at 2 theta value of 38.43 is just because of the two parallel planes in the crystal 1 1 1. So 1 1 1 plane of one unit cell and the another unit cell, those are parallel to each other. They will act as a mirror like plane and they will diffract the X-rays which will be constructively giving out a reflection pattern. Now you can see that you can from XRD to theta values you can determine HKL values. Can you determine A? Yes, we can determine A. What is A? A is the length of unit cell volume, unit cell. So how it can be done? We will just use another formula that is already used by us. Now you can go back. This formula we have taken it from reciprocal lattice concept. Now you have HKL value for that particular peak having D spacing, certain D spacing. You can calculate A. It is very simple. Okay, now we will go ahead with this problem. Okay, who will calculate for me? Yes, D spacing. How to calculate it? We can go here. Okay, sin theta is 0.3291. Theta is something like this. N lambda is equal to 2d sin theta. So I will write it here. N lambda is equal to 2d sin theta. You have with you sin theta value you have. Sin theta, how much sin theta is there? 0.3291. So I will just write it, copy and paste. Okay, here. Lambda is equal to 1.54 angstrom. 1.54 angstrom. 2 is 2. D we don't know. Sin theta is 0.3291 into 0.3291. What you can do? You can take all these numbers at one side of the equation. Okay, now 1.54 divided by, you can write it in this way, control C, control V, okay. 1.54 divided by, in bracket, 2 into 0.3291 is equal to D. So what will be the value of D? That will be in the angstrom unit. Who will tell me what is the value of D? Yes. Now you can do it. So we will do it here. Okay, 1.54 divided by 2.77. Then you divide it by 0.3291. D value will be 0.339. D value will be 0.339. So I will write D here. So, okay, we will just use this one. Sorry. Okay. D value is, so you can have D, control V. D value is equal to 2.3397. 2.3397 angstrom unit. Angstrom. Now what you have to do is that you have to recall that formula. Control C. Okay. So delete. Just a moment. Okay. This is the formula where you know now D, HKL is 111. So what will be the, this equation will become something like this: 2.3397 1 over 2.3397 square, is equal to h square plus k square plus l square is 3. So 1 plus 1 plus 1 is 3 upon a square. So now you take this value to this side. So I will do it. Square of this 5.474 into 3, it will be 16.422. So you will have a square something like this here is equal to, so this will go to other side of the equation. So this will become, a square will be 16.422 angstrom. Now this is the square of a. So a will be square root of this 16.422. Take square root. It will be 4.052. You can see that A of aluminium. A of aluminium is equal to 4.052 angstrom. 0.52 angstrom. Now you can go back to your knowledge. What is the formula for the cube volume? This is A. Now, if you know the trigonometry, volume of cube phi is equal to cube of A. This is very simple. We can say that formalism that we can get from the, you can see that volume is a cube. So you make a cube of it. So cube of it, can you do with this one? Oh, I don't have on my this one, but okay, we can just show scientific, okay. Square it and then multiply it with 4.052, 4.052. So you will have 66.54. The answer will be 66.54 angstrom cube. Angstrom cube. So students, now you might have understood that from simple XRD pattern you can determine HKL values. You can determine HKL values. These HKL values you can determine from simple XRD. You can determine sin theta. From sin theta you can determine D. From D you can determine A. From A you can determine volume. And now from volume you can determine density. How? Density is equal to mass by volume. Now you know the volume of small unit. If you know the mass present in that smallest unit, you can calculate density. Now how to do it, I will tell you. Now if you are, we will go back. Now we will go back to initial system that those we have discussed. Okay, we will take primitive cube first. So this atom at the corner is 1/8 part of this unit cell. So there are 8 corners. At each corner there is an atom. So total atoms present in primitive cell is 8 corner into 1/8 part of that atom of this one is equal to 1 atom. So if your simple cube system or primitive cube system is there, your unit cell will contain only one molecule of your compound or one atom of your compound metal if it is element. In face centered cube, you have 4 atoms of your compound. If it is body centered cube, 8 plus this inside one, 1 plus this inside one, you will have 2 atoms. In total, 2 atoms are contained in body centered cube. In total, only one atom is present in the primitive cube. In total, 4 atoms will be contained in a face centered cube. Now we will go back to our calculation. Now we don't know whether our cube is body centered cube, primitive cube, or face centered cube. So we can arrive that information. We have certain rules for those identification. So instead of going into details of those rules, you can just keep a trick in mind. So I will just give you so many tricks. So if your cell is primitive, primitive means only one atom is there. There is no rule for reflection. All sorts of HKL values can be appeared. But if your cell is body centered cubic, all the HKL values that HKL will be 2n. So now in our case, first HKL was 1, 1, 1. So if you add 1 plus 1 plus 1, it is not equal to 2n. It is a fractional value, 1.5 we will get. So our cell is not body centered cube. If it is face centered cube, that HKL value either all odd or all even. For example, it should be 110 or 111 or 200 or 222, 222, something like this. So there should not be 210 kind of reflection present in our sample if it is body centered cubic. This is one trick. The second trick you can keep in mind, first reflection of primitive is 100. The first reflection of body centered cubic is 110. First reflection of this face centered cubic is 111. So this is simple trick that you can keep in mind, but it will not be always true. 98.8% it will be true, but in some cases there is a complexity is there for this rule. But this rule is always true. But you can follow either of the rule. So in our case, first reflection is 111. You can see that either all odd. Yes, H is odd, K is odd, L is odd. All three numbers are odd. So our system is FCC. Now what I told you, in FCC, how many number of atoms are there? 4 atoms are there. Now 4 atoms are there. You understood from the calculations. Now we will go here. I want to calculate the density now. How to do it? Density rho is equal to mass present in that smallest volume divided by volume. How many atoms are there of aluminum? 4 aluminum atoms are there. But mass, atomic mass is always presented in atomic mass unit. Volume, in our case, volume is presented in angstrom cube. Angstrom cube. And the density is always given in cc per gram. Cc per gram. Gram per cc, sorry. Gram per cc. So now what you have to do is that you have to convert this. Aluminum is having atomic mass number 27 in my opinion. Okay. You can check it in the periodic table. So you can multiply 4 with this 27 and that is an atomic mass unit. Then convert that atomic mass unit into gram, or you can just use Avogadro's rule. So 27 something is there, gram is equal to that Avogadro's number. So 4 number, how much is there? You can multiply or divide and then you can get. Now we'll go ahead whether we have those kind of calculations here or not. Okay. Okay. 19.3 gram per cc. Okay. What you can do is that you can see that this is a sum. So you can have 27 into 4 because 4 atoms are there in a face centered cube. Divide it by Avogadro's number and then multiply it with volume. Volume is in angstrom cube. So you, to convert it into centimeter cube, you can have 10 raised to 8 angstrom. 1 centimeter is equal to 10 raised to 8. So centimeter angstrom, if you have to convert 1 angstrom is 10 raised to minus 8 centimeter. It is a cube, it will be minus 24. So you can just get the density at last 19.3. So how to get it? So 27 into 4 divided by this number 6 not 22. This is Avogadro's number. 27 is a molar mass of aluminum. So I have taken 27 gram. But 27 gram is not present in my unit cell. Only 4 atoms are there. So I have to divide it with this number because this number will give me the mass of one aluminum in gram. 10 raised to 23. So you can make this calculation. So this 23 is there. So this is minus 24. So you can just take this as a 6.744. You can just make the calculation. So we will make this calculation. So you can have 27 into 4 is equal to 108. Divide it by 6 point not 22, not 22. Okay. Then divide it by 6.714. Divided by 6.744. So 2.659 is the density. So 2.659 is the density. Let me check. 67 is what is the volume of our system? 66.54 is there. So this 67 may be for different this thing. So we can do it. Let me check the aluminum weight. So weight of aluminum is something 27. Okay, it is not given 28.9. It is 27. 26.9 is 27. So 27 into 4, something like this, divided by 6.022, then divide it by Okay, where is the formula? Then divide it by 66. Divided by 66.54. That is the volume which we have. Into 10 you can do. Into 10. That is minus 2.7. So you can just Google it out. So you will understand whether our solution is correct or not. So 19 point is the answer for gold. It is not for this one. So what we have obtained from XRD, you can see that. Just to summarize, you calculated the spacing, you calculated lattice size A, that is length of the cell, you calculated volume of the cell, and at last you calculated the density. So what is it? Density is 2.7 something. So you have calculated HKL values also. Now I think, okay, let me check whether there is any example for you or not. So, okay, this is another system. Okay, you can take this as an example for you. You can have homework with this one. This is the X-ray diffraction pattern of gold. So you can take the 2 theta values. You can solve by your own. You can take a snap. You can take a picture from your mobile camera. You can solve. What you can do? You can find out sin theta, theta, sin square theta. You can find out D. You can find out A. You can find out volume. And then you can find out density. How? You have to find out the HKL, and from that you have to decide whether it is a primitive cube, body centered cube, or face centered cube. And then you can determine the density of your material. I think up to this point, uh, is it okay for you to understand this, or should we repeat with one of the example? Yes. Is it okay for all of you, or should we solve any other problem of this kind? Okay. Now you can calculate the calculate for your response, and then we will start the special applications. I will teach you again how to make a model of your own material. Then there is one XRD pattern somebody has shown me, sent to me. So this is something AGX10, AGX10. So if somebody will raise his or her hand who has sent this sample, I just need the information about the elements, which elements are present in that AGX10. Something is there. Somebody has sent me this XRD pattern, AGX10. So I want to have some information, chemical information about this sample, so that I can
Gita,
teach you.
it may be silver oxide, sir.
Silver oxide.
Yes.
Okay. Is
Gita
it?
madam, 1 second. Gita madam, please share the name of the material whose XRD you have sent. Please write in a chat box.
Yeah, yeah. So I can tell you how to identify the or match the XRD of this. If you don't have JCPDS cards with you, you can create your own JCPDS data by using open sources, so that you can confirm your material is Ag oxide or Ag chloride or Ag nanoparticle. I guess that this may be Ag nanoparticle that might have synthesized by some bio methods. So I'll wait for her response. At the same time, we can just draw the graph of this particular material. She has sent me a data, and I have selected only X and Y values of those data. Now we can plot the graph. There is some problem, so we can just take that. Okay, delete column. Okay, Control C. Now we can just draw the graph. You can see that. I think this is zinc oxide something, my first opinion. So is there sample information available? Let us check. Okay, nobody has shared this particular sample information. But if Ag is there, we can just check whether Ag is there or Ag oxide. So for this, what you have to do is that you can either download. Oh, sorry. Stop. You can download the program called Mercury. Mercury is a free software, or you can download a program called as Vesta. I can just type the name of the softwares in this chat box. Vesta. JP Mineral is providing this. JP Minerals. So you have to only give your mail ID to them and you can download. Another software is Mercury. These two softwares can be used to draw a crystal structure out of your XRD data if you solve the crystal structure. Secondly, you can simulate, means you can theoretically calculate XRD of any material, known material. For example, TiO2 is there. You can take crystallographic information available in the literature, you can feed it to these softwares. This software, uh, in this software you can also put the input values of lambda. For example, we all use 1.54 many times, but by chance sometimes somebody use molybdenum or cobalt. That input also you can do, and you can simulate the XRD pattern. Now I will just simulate. I think there is some problem to this one. Just a moment. Okay, AG extend. Okay, now what you have to do is that you have to download one of these software. Now I will take direct you to the website crystallography.net. Okay, don't go into detail of these colors. So the European countries are supporting Ukraine, so that is why this Ukraine national flag color is there. COD, crystallographic open database. So this database is similar like JCPDS or PCPDF win card. When you write a paper, the referee will always ask you about that JCPDS card number. So now in your case, if you don't have DCPDS card database, you don't have to worry about it. What you can do, you can go to this website and you can go to the search button. So I will go to the search button. So now in my sample, I first believe that this is a silver oxide. Ag, I will write, and then I will write oxygen. In my sample, I will tell to this website that my sample is there, and in it silver and oxygen is there. I will tell that only two elements are there. Now I will send this query to the server of the website. The website will suggest me several files having silver and oxygen as a content in this database. Now we will see whether there is a database or not. It is taking me to the, okay, it is AGO and AG2O or AG2O2, AG2O3, AG3O4. So you can see that. I hope that this is visible to you. So this website is giving so many compounds of silver and oxygen to me. But if I know that it is a Ag2O, if I know the experimental condition and my silver is only 1 plus and there is no chance for the silver to get oxidized, I will always believe that my compound will be Ag2O. So now what I will do, click it on the CIF. So this CIF file will be downloaded here. Okay, 1010604, this is the number. This you have to give. If your XRD is matching with the data, you can give this number, and you can write COD 10 10 604 is the reference of my sample. This is the reference. This is YCOP RWG, crystal structure of silver oxide, published in American Journal of Science series in 1922. You can see that.
Sir,
184 and 188 is the page number of this paper. Now I will open this file in a Mercury. You can open it in another software too. Okay, this is a silver oxide. You can go to this tab, calculate powder pattern. Okay, it is calculating powder pattern. I will just customize it. Customize means wavelength is 1.5406. I want it from 10 to 80. So whatever range we have selected in our experiment, that you can give it here. Okay, 10 to 80, I got 4 peaks. Now it is time for me to save this XRD in soft XY file. Download AG20 XY. I will write it like this. Save. Already it is there, so I will replace it for your sake of convenience. Now you go here, take another window and bring that data. I have saved it in download. Then go all files. So silver oxide file will be there. Copy it and take it to the earlier data, that experimental
sir,
data I want to match.
sir.
Huh.
The material is silver dope ZNO, zinc oxide.
Okay, okay, sir. Okay, now we will go back again. Okay, okay. Thank you for clarifying it, because it would have taken a lot much time. Now we will go back to this website, and now we will change our search. Zinc oxide, it is there. Now you go back. So I had predicted it because of its nature. So if you have zinc oxide in your sample, you can see three peaks in between 30 and 40 always. Okay. Now that you can get it from your experience. Now we go back to this crystallography database, zinc oxide. You can see that several files are there, but many files are having zinc oxide. So you can just take CIF of one of it. I had taken this one. So file number is 10 11 258, and this is the reference number. You can put it into the reference of your paper. So nobody will question you. Now I will open this file. Okay, this is zinc oxide. You go to the calculate again, powder pattern. Now you can see here, you can go to the customize, because I don't want this range. I want 80 and 10. Wavelength is okay for me. I will not change here. You can change wavelengths here. You can have different wavelengths or type here. Okay, okay. Then save it as a zinc oxide. ZNO. In download, I am saving ZNO. You can see that. ZNO download. Save. Yes. Replaced. All the files are replaced. Now I will go back to this data set. Delete it. Earlier one. Okay, I will get all sorts of files here. Okay. Okay, this is a zinc oxide file which I have simulated from the software. This is my experimental data that has been provided by the instrument engineer or operator. Now this axis I will make it as a x-axis, because this is a x of another calculated XRD. Now you overlap it with each other. You can see that. You can see that so many lines are matching with zinc oxide. So these three lines are matched. This line is matching. This line is matching. Little bit difference in peak position is there, because my wavelength may not match exactly with the wavelength that you have used. If your file I will see, I can put that correct value of lambda, so that it will match very clearly with it. Now it is duty for me to identify these two, and there is one more peak here. Which one material is there? Now if this material is heated, there is a chance that silver can get oxidized. Now I have silver oxide peak already simulated. So I will open that file. This is AG20 we have already simulated. I will copy this also. Ag2O. I will take it to this data sheet. So I know, I hope that all of you know the operation of this origin software. So here I will put the silver oxide. Now you can write the names also if you don't want to get confused. Ag2O, yes. Then this is a zinc oxide, and earlier unnamed is your sample. Now you can see that. Yes, it is matching, but the problem is there. Another one peak is there that is not matched. So I have to check, is there any other silver compound is there, or okay, there is some difference is there. So this much large difference into theta is not acceptable. So I have to check whether there is one more compound of zinc and Ag and silver together can form. So you go back to this website and ask a new query. So zinc, Ag and silver, I will put the three elements at a time. It will restrict its search within the database of zinc, Ag and O. Or you can have to, you can search Ag2O, AgO2, AgO, something like that. That is also possible. So there is no single compound that is made up of Ag, zinc and oxygen. So now I will have the AgO file. So what was the temperature of heating? If it is very high, then only it will be oxidized to 2 plus or any higher case. So you can just make your search continuously so that, okay, Ag2O we have already matched. Now we can match AgO. We'll just check this one, and then we will go to the next application. So I will just do it in 1 minute. Calculate XRD pattern. Now we have chance to, okay, 0.18 I will write actual wavelength. 80 is the 10. 80. Okay. Save. So I will save it as a Ag2O. It is already there, Ag2O. Okay, save. Okay, now you can bring that Ag2O files here. So we have already opened it here. Okay, bring it. So export it from this one. Okay, Control C. Okay, now you can paste it here. This I will delete. Oh, it is AGO actually. Now also there is a little bit chance that you have AGO. So you have to keep on trying so that somewhere it will get finished. So now I don't have any information, clear information about the synthesis. If I will get the information about the synthesis, I can easily find out the other phases in my sample. So this is trial and error, little bit time consuming, but it will increase or enhance your confidence level. So that without having any paid database with you, you can analyze or identify the compounds present in your sample. Now, what we can do is that we can just see the other applications. So I will just introduce you with a new software that is called as a JP Vista, that is provided by JP Minerals. So I will just search it in the website for you. JP Minerals Vista. You can only Google these letters. So it will be directing to you to this website. It is a website that is running by the Japanese Association. So you can download it based on your Windows system. So there are different versions on it. So you can just take copy and paste it, download it, and then copy and paste it into the D drive or C drive, wherever you want. Now I have already with me this particular uh, files with me. So I will open that Vista. Vista. Okay. So I will open this software now. Okay. Close. So it will open something like this in your system. Now, if you want to make a model, crystal model of your compound, you can just open the crystallographic information file that we have already downloaded. Now I have downloaded two files. AgO file is there, zinc oxide file is there, Ag2O. I will use zinc oxide file now. So open, this is a zinc oxide. You can go to here, edit. You can edit bonds, lattice planes, everything. You can change the properties, you can change the boundary, means you can make it bigger crystal. Okay, 2 apply, so it will be very big crystal now. So it is very easy tool. In 5 to 10 minutes you can make a model if you have little bit knowledge of this system. Okay, so it is a tetrahedral geometry around the zinc. So oxygen is tetrahedrally getting coordinated with the zinc. There is kind of models you can make, and you can make your data that you want to present in your thesis or paper more, we can say it attractive. So you can change the colors. So many colors are available there. So you can just use either, based on your choice, you can use any one of it. Okay. Okay. Now what we can do, I have something to okay show you some. Let me check. Okay. Now we will go back to presentation. No, no. Ah, पुढून ये इकडे. Okay. Yes, sir. या इकडे. मगाशी ऑनलाईन चालू होतं म्हणून काय डिस्ट्रीब्यूट केलं नाही. So you can take another example for homework. So you can just take a snap of this slide. So it will enhance your confidence level. So you can also take the snap of this particular picture. So it has one more example in it. So the times you do this particular exercises, that will enhance your confidence level. In any instrumentation, if you want to train the expertise, the only thing that will make you an expert is the your exercising or practicing way. So if you'll meet n number of problems, so you can just take the snap of this also. This has a procedure of indexing in simple manner. Okay, now okay, after discussing so many things, if somebody have not understood anything out of this discussion, so for that individual I am always placing this slide at the end of my talk. So XRD pattern, the peak position will tell you about the unit cell dimension, that is D spacing, cell length A, volume will be controlled, or that will be reflected into theta positions of the peaks. If there is any line, now you have seen already that zinc oxide peak profiles were matched, but there were some extra peaks in your sample. So those lines were non-indexable lines. That indicates presence of a crystalline impurity or incorrect way of indexing the XRD pattern. So that is why we have to do the exercise to find out the actual phases in your sample. If some peaks are absent, for example, in our material only first peak was 111 and 100 was absent in aluminum XRD pattern. That tells as systematic absence of 100, 200 is because of the symmetry. So background, if I have not shown you background, in maybe next PowerPoint presentation I have 10-15 minutes, there I will show you this. So if background is heavy, so that tells you amorphous material is there in your sample. If your XRD peaks are very sharp, your material is highly crystalline. If your XRD peaks are broad, either your material is nano sized material or it has a stress or strain in it, or there are stacking faults present in your sample. Peak intensities will tell you about the distribution of the atoms within the lattice. So if the plane containing the heavy atoms are there and if it is positively contributing to the X-ray diffraction intensity, so intensity of that peak will be very high. So in XRD, the intensities diminishes when you go from smaller to theta to higher to theta. The X-ray diffraction peaks intensity will get diminished. So that is just because of the phase difference. So when the phase difference is directly proportional to the sine theta upon 4 lambda. So sine theta upon lambda. So the applications of X-ray diffraction, we can discriminate material either it is crystalline or amorphous. We can determine the crystallite size, that we will do it in 10 minutes. We can calculate crystallinity of a sample if you have series of samples. You can find out the kinetics of crystallization of a material by recording the XRD pattern at different time interval. You can find out the phases present in your sample qualitatively. Now we had done qualitative analysis of your sample. So that is qualitative analysis. If I can tell you how much zinc oxide is there and how much impurity peak is there, in percent is there, that is a quantification. So you can do that. So this is the only method that can be used to quantify the phases of any compound present. For example, if TiO2 is there and if you have mixture of anatase and rutile, if you will go for X-ray fluorescence or if you will go for chemical analysis, AAS, ICP, that will never tell you how much anatase, how much rutile is there. XRD will tell you how much anatase and rutile is there, because that will produce peak at different positions. You can find out the expansion or contraction of lattice as a function of doping the impurity. For example, if you are doping zinc oxide by silver, now you can just check size of zinc will be different than the size of silver. So if you are replacing smaller size zinc by a larger size as silver, there will be expansion in the lattice. If the lattice will expand, d space will be increased. So that can be reflected, in your peak positions. If your structure will get transformed into new structure, for example, if cube is converted into tetragon, so if tetragon is converted into orthorhomb, the XRD pattern will be changed little bit, or new peaks will be arised in the XRD pattern. So that can be studied by using powder X-ray diffraction. Chemical reaction studies, for example, if you are doing solid state synthesis BaO plus TiO2, you can track that synthetic reaction at what temperature, after what time BaTiO3 is formed. So that kind of reaction tracking you can do by using in situ X-ray diffraction studies. X-ray diffraction is a rapid and non-destructive analytical tool. Rapid means fast. There are certain machines which can only spend 1 or 2 minutes for data collection. Non-destructive means you can get back your sample without getting damaged. Organic samples sometimes have chance to get damaged because carbon, if temperature or time of exposure is higher, so if delicate molecules are there, those will get decomposed, or the photosensitive organic materials will get decomposed. But for inorganic material, it always stands as a non-destructive tool. You can get back your sample and take it to the another characterization machine. The requirement to grow single crystal is eliminated if you use powder X-ray diffraction, because sometimes it is very difficult to grow single crystal of enough size. In that case, you have advantage of this powder X-ray diffraction. You can go for the microcrystalline polycrystalline material and you can index it. If you are successful in indexing, you can also determine the crystal structure of it. With special equipment, very small samples may be used, 1 to 2 milligram. So that is called as a point focused or focusing X-ray diffractometer. So there are so many machines, those are using this one. Okay, you can see that I have already told you that I will tell you about the background and amorphous material. So if you are new to X-ray diffraction, you will confuse that whether these three spikes should consider peak or not. In my opinion, these are the spikes, these are not peaks. So it is your wavy background. So if you will get smooth, if you will smooth the data, so it will resemble like this one. So these are not peaks. Peak, you have to mathematically define it. Intensity should be double of the background intensity. So at least this much spikes has to be there, then and then only I will consider it as a peak. So this is because of amorphous material. So this hump is there. This is always there in amorphous material. So you can determine amorphous. So in some cases, if your crystallite size is less than 2 nanometer, if you are preparing quantum dots, and if the size of the particle is less than 2 nanometer, the XRD will look like this one, because the size of your particle is so small that cannot take part in diffraction. You can check sample purity. We have already checked it. Crystalline material will show you well-defined XRD pattern. Just I will take 1 minute break and then we will start the. I will just tell you the list of softwares that you can use for your uh, research tools.
Sir,
So
we have a session at 3 p.m.
3 p.m. Okay. So should we break at 2:30?
As per your choice.
Okay. In 5 minutes, I will just to show you, your students some websites and some software and some special application I would like to mention here. I will
Yes, sir.
just mention it in one sentence only. Okay. Okay, you can calculate crystallite size, not particle size from XRD. Here D is a crystallite size, K is a constant. If your particle is spherical, this is 0.9. Lambda is the wavelength that you are using for experiment. This is a beta, beta cos theta. Theta is the angle. The peak which you are selecting, that will have 2 theta value. Divide it by 2, you will get theta value. That theta you can put it here. Now this beta is the corrected width of the peak at half of its height and okay, FWHM, we call it as a full width at half maxima, but this beta has to be corrected for the instrumental broadening. Instrument itself will have its own broadening that you have to subtract from the broadening of your peak, and then you can calculate very accurately the crystallite size of your sample particles. The crystallite size, if it is equal to the particle size that is determined by TM, then your material is a single crystal material. So if you will have spherical particle in powder XRD, there will be no problem. But if you will have samples like this one, rod-like samples, certain directions will be exposed for the X-ray diffraction, and certain direction planes will not be exposed fully to the incoming X-rays. So this is zinc oxide. You can see that all these samples are zinc oxide, but these samples are there in which rod shaped geometry is there. So only the intensity of middle peak is enhanced. So other two peaks intensity is, we can suppressed. You can say it is suppressed because of the preferred orientation problem. That is why when you are collecting X-ray diffraction data of your powder sample, you can spin your sample continuously. For example, 30 rotation per minute, 20 rotation per minute speed you can give. Sample will rotate so that it can remove this orientation problem. So then you can get the expected. You can see that this is a rod shape geometry and it is having huge problem of intensity distribution. This is a bulk sample with a spherical particle morphology, but in rod shape morphology you can getting enhanced intensity of certain peaks only because of their orientation, preferred orientation. So you can remove this problem by rotating your sample during data collection. So if you are not specialized expert in this field, you will never understood what is the problem. That is why it is always recommended that you rotate your sample or spin your sample during data collection. I think there are lot many applications we can discuss, but time is limited. So, if you have any problem related to this topic, you can always ask the questions via email, or my phone number is there with Ahire sir and madam. So, I will be very happy to get queries from the students regarding their interpretation. So this is the one more specialized application. You can put your battery here, and this is the X-ray beam that is coming here, and there is a plate type of detector is there. You can charge your battery continuously or discharge it continuously, and you can probe the changes those are taking place during charging and during discharging in your electrode material. So we call it as the in operando XRD studies. You can have in situ XRD studies. So some peaks will change their position, some will disappear, new peaks will appear. So that will tell you about the structural transformation. So you can identify clearly the compounds in the literature, whether if you follow certain. So this was the paper that was reporting zinc, silver, antimony oxide. So I wanted to prepare it and I wanted to solve its crystal structure. But when I re-examined the XRD pattern of it, I found that this material is nothing but the silver chloride. So you can also place the commentaries in the literature, because the data can be cleaned. So you can solve the crystal structure from powder XRD. So that is another story of this particular one. You can do ritual refinement. You can uh, determine the composition of mixture of 6-7 compounds at a time. So thank you all of you for your patience listening. Now session is open for the discussion.
Participants are requested to put your questions in Q&A section or chat box, or you can raise your hands so that you can talk in the webinar also.
Yes, I can share my number here so that students can, if they don't want to ask queries openly, they can email me if they have any queries regarding the talk, as well as if you want any kind of help to interpret your XRD data. You are always welcome. Actually, offline sessions would have benefited the students more clearly, because I have limitation to write and dictate here on the screen.
In future, we'll definitely try.
Yes, sir. Yes, sir. I think no queries are there. So,
Rima madam?
okay, free softwares, I will post the website here. ccp14 dot uk. This website is there. You can download so many softwares which are free of cost. But for XRD, GSAS, then Mercury and Vesta is more than enough. Then Expo 14 is there. That is from University Bari. University Bari. So you can download and use those. So the application which you want, that decides which software you have to use, because most of the softwares are not unique. They are specially designed. The first two softwares are for ritual. Okay, sir, you can conclude. Thank you very much for uh, allowing me to present my session here on this dashboard.
Okay, thank you, sir, for giving an informative talk about the XRD, fundamentals of XRD, and how to work on this XRD data. In future, we'll definitely arrange your lecture in offline session also. So thank you
Yes.
on behalf of MGV's Arts, Science and Commerce College,
Thank
Panchavati,
you.
Nashik.
Thank thank you, sir. Should I
Thank you once
share
again.
these slides with you?
Yes, sir.
Okay, sir. I will email you.
Yes, sir. Thank you. I will shared it with participants also.
Okay, sir. Okay.
Thank you, sir.
Thank
Thank
you.
you. Participants are requested to join the research methodology session at 3 p.m. on the research methodology link